Hello everyone, I am Nitesh. I am a PhD student at University of Wisconsin-Madison. Today I will present my work on elastic instabilities in soft fiber composites. I will discuss the factors influencing the onset of instabilities and the associated pattern transformations. As we all know, fiber composites are commonly employed as structural basis for building not only man-made materials such as carbon fiber reinforced composites, but also by nature as biocomposites in tissues and tendons. The reason behind their wide application is that they simultaneously provide many desirable mechanical properties like toughness, rigidity, lightweight, and flexibility. However, because of the heterogeneities involved, they are also prone to many instabilities as listed. Here I am going to focus on soft fiber composites. These composites are capable of undergoing large deformations and predominantly develop buckling of fibers. Now, what is the motivation to investigate instabilities? Historically, instabilities has been regarded as one of the failures. However, it also leads to the transformation of microstructure. Moreover, it is elastic or reversible in nature. That means when the load is removed, the microstructure reverts to its original configuration. This gives an opportunity to design materials with switchable functionalities. For example, acoustic metamaterials with band gaps, soft gripper to enable optic materials, and also auxetic materials. Apparently, the key factor in these applications are the patterns that we get post-instability. Here I will consider the factors that dictates the buckling patterns in soft fiber composites. That includes material properties of soft constituents, then there are geometric factors. Among these, I will focus on the influence of phase stiffening and the fiber arrangement. Starting with composites with stiffening phases. We consider periodic fiber composites with a square arrangement of fibers, represented using the unit cell. The composites are compressed along the direction of fibers. The phases show stiffening behavior which is captured using the Gent strain energy density function. Here J is the locking parameter which captures the stiffening effect. Smaller the locking parameter, higher the stiffening. We observe that the instabilities occur at higher deformation levels as the value of fiber locking parameter increases. Moreover, the wave number of the instability pattern also increases. The buckling modes of fibers shown here highlight the significant variation in the wavelength even for a small change in the locking parameter. Next, we investigate the influence of fiber arrangement. Previously, we considered the same distribution of fibers along the two principal directions. Now, we will consider unequal distribution represented by this unit cell. Geometrically, these composites are defined using the fiber volume fraction and additionally the aspect ratio. Here is an example of finite specimen. Clearly, the fibers are closer to each other in one principal direction than the second one. Now, the question of interest is, in which plane the fibers will buckle? Plane 1 or plane 2 or maybe somewhere in the middle? Simulations predict that the stability of the composite decreases with increase in aspect ratio. Interestingly, at smaller values, the fibers buckle towards the stiffer direction, that is, the direction along which they are closer to each other. At higher values, however, the fibers buckle along the second principal direction where they are far from each other. And in the middle, there lies an intermediate region, shaded in green, where they buckle along a non-principal plane. The findings are also validated by experiments. Moreover, the wave number decreases with increase in aspect ratio. This scale shows the variation of plane orientation with aspect ratio. Now, let us see the buckling of fibers observed in experiments. At aspect ratio 4, the fibers buckle in plane 1. At 10, they buckle in plane 2. And in the middle at 7, buckling is observed in both planes 1 and 2. This indicates the buckling towards an intermediate or a non-principal plane. In summary, we have seen how the instability patterns are highly tunable by the properties of constituent materials and the in-plane periodicity. These findings will further widen the design space for building materials with switchable functionalities. Thank you for joining. For more details, please see the longer version.